Hello, this is the third video in the Graphs and Network 2 series for OCR Discrete Further Maths. It looks at finding a minimum spanning tree using Crisco's algorithm. We have already seen Prim's algorithm for finding an MST in the previous sessions. Prim's algorithm built on MST in a connected way. If we were to find an MST purely by inspection as human beings, we might scan the network diagram and focus on the shortest arcs. For small networks, we could solve these in our head. So first, we might decide to choose the shortest edge. In this case, this would be ED with a value of 6. We might then search around and spot that the next shortest value is AC with a value of 8. So you can see that this jumps over around the network and doesn't necessarily build the MST in the same organized, connected way that Prim's algorithm did. So although Crisco's algorithm will find the same MST as Prim's in terms of being a minimum weight, rather than adding arcs in a connected way, it is much more chaotic. This algorithm was first published in 1956 by Joseph Crisco. It is another example of a greedy algorithm. Let's work through this example of Crisco's algorithm with a network together. The first thing you have to do is to select the shortest edge in the network. This is WL, which is of value 5. After that, the next shortest one is CL with a value of 7. This looks like it's building like Prim's, but actually it doesn't have to be connected. Subsequent to that, choose SR with a value of 11. We now just have to connect the CLW to the SR, and we could either do that by choosing SC or CR. It doesn't really matter. Let's choose SC. We now have a minimum spanning tree with a value of 35. You will notice that this has the same weight whether we obtain it via Prim's algorithm or Crisco's algorithm. Here is another example. You may wish to pause and try this for yourselves. Remember, when you're carrying out this algorithm, to list the edges in the order that you select them and write the total weight. It is really important that the order indicates whether you're using Crisco or Prim's algorithm. So, scanning this example, you will see that the shortest length is DE. Then FG, then CD, and DB, followed by EG, AC, and finally HG. With a larger network, you can see that we did jump around a bit more, so it wasn't as connected as Prim's. If we were to add these all up, we would find that we had the same total weight as if we had used Prim's algorithm of 174. Because we did not have any choices between two arcs to make, we'll also find that we get exactly the same MST as via Prim's algorithm. The common errors when we apply this method are either not spotting the shortest arc to start with, or forming a cycle by mistake, or forgetting to record the order of arcs as we go along, not showing enough working, or forgetting to state the length or weight of the MST at the end. If we are to compare Prim and Crisco's algorithms, then although both algorithms are greedy, both find the minimum spanning tree, but the arcs will often be added in a different order. If there is more than one MST, in other words we have more than one choice when choosing the arcs, the two algorithms may find different MST. Whilst Prim's always joins a new vertex to an old vertex so that every stage is a tree, Crisco's allows both new to new and old to old to get connected, so it risks creating a cycle and one must check that every time. Crisco's algorithm cannot be used on a matrix or table. Thus, whilst it was good for small networks, it is not easy to program for a computer to deal with larger networks, and Prim's is preferable. In the next session 2.4, we will look at an algorithm to find shortest path.